keep it real with it most. Marcy, broke down.
Hi, I'm Juha and I'm a hockey player here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard. Here I have recapped the two important results we got previously, and let's see what we can do with this. So let's start with the definition of velocity. That is a derivative of displacement with respect to time. So let's go on and integrate this whole thing. So in order to do that, we have to separate the dt or the d term. So we'll move the dt to the other side first, like this. And now we go on and integrate both sides with respect to the d terms, whatever they are. So on the left hand side we are integrating respect to time, so from some initial time to any given time we are integrating Vx, and on the right hand side our variable is just a displacement, so we go from some initial displacement to some displacement x at time t. So this is how it works. At time t0 we are at x0, and at time t we are at position x. Right. So we don't have to do anything on the left hand side, so we just keep it as it is. We can't do anything because we don't know what this Vx actually is. It doesn't have to be constant, it can be changing. But on the right hand side we are just integrating a constant, which is in fact 1. So what we get is x, and if we evaluate this one, let's bring it on the left. So we get x minus x0 is whatever you had on the left hand side. And once more bring the x0 to the other side. This is still intact. So what do we have here? It says that if we know the function or how the Vx behaves, we can get the position of the object at any given time t by using this formula. What you would have to do is to integrate the velocity function over time and then just plug in the value, let's say at the instead of 5 seconds, for example. Alright, same thing here. What do we get from the acceleration? So again, we separate the variables to their respective sides. And on the left hand side we integrate respect to time from t0 to some arbitrary t. We integrate the acceleration this time. And on the right hand side we are just integrating the velocity. From some initial velocity to some arbitrary velocity at time t. So nothing happens on the left hand side again, because we don't know what this ax is. It can be changing in time as well. But on the right hand side we only have constant term, so integrating from v0 to v some velocity like this. And again switch things around, left to the right. So evaluating this expression we get v minus v0 is integral from t0 to t ax, and then just bring the v0 over to the other side. So now we have expression for the velocity if we know the acceleration at any given time and we have some initial velocity. So what do we have here with these cryptic looking integrals? So let's backtrack the whole thing. So let's imagine that we can keep track of the acceleration at all the time. So if we know acceleration the whole time, and we also know the initial velocity, let's say it would be 0, for example. As long as we know the initial or the acceleration the whole time, we get velocity at any given time by integrating from t0 to this any given time t. And now that we know the velocity the whole time, so this is, by the way, in the x direction, of course, like this. Now we know the velocity, we can plug it into this formula, and now we integrate from over time again. And by knowing our location to begin with, we get our location at any given time. So this has a practical application, of course. For example, when we are measuring, or we know the acceleration of any given time by measuring it using an accelerometer. And this is how inertial guidance systems work. Because we all, at any given time, we know the value of acceleration. We keep integrating it using the computer, which gives us velocity at any given time. And integrating again, we know our location the whole time. So, in fact, you don't need satellites guidance systems to keep track where you are, as long as you are aware what is your acceleration at any given time. And I will show you in the one of the example videos how can we, by using these two formulas, to get the actual position data in the case when the acceleration is constant, just to make things simple.
I'm feeling it.